Welcome back. I'm Dr. Michael Steiner, and I work with Dr. Ronald Rendell on the investigation of the measurement problem. The title of this video is the Measurement Problem 5, Historical Perspective. This is the 5th video in our Quantum Measurement Problem video series. Our Measurement Problem video series is designed as a complement to our book, The Quantum Measurement Problem. In this presentation, we will examine the measurement problem from a historical perspective. We will begin at a time when Greek philosophers were considering fundamental scientific problems and work our way through the classical physics era of Maxwell, Newton, and others, and lastly to the quantum era of Bohr, Einstein, and others. There are many subject areas that are related to the measurement problem, and we will try to touch on several of these in the video. However, the viewer is referred to our book, which considers these areas in more detail. The Greek philosophers had considered several fundamental issues of physics related to the measurement problem as early as the 5th century BC. Here we will consider Leucippus, Democritus, Aristotle, and Epicurus up until 270 BCE. Little is known of Leucippus, who originated many of the ideas held by Democritus. It is believed that Democritus was a student of Leucippus. In Democritus's writings, we find the idea of atomism. For Democritus, matter exists in solid, indivisible elements called atoms. Atoms are indestructible and are homogeneous but differ in size, shape, mass, position, and arrangement. Solids, liquids, and oils have different sizes and shapes. Democritus believed that the motion of atoms was predetermined. Luck, chance, or non-determinism do not exist at the physical level, but are just macroscopic effects that cannot be predicted because of the complexity of the situation. There is an exception to this rule that Democritus considered, which was that the movement that separated and arranged the universe in its present order came about by chance. The next major philosopher that arrived on the Greek scene was Aristotle. Aristotle rejected two major tenets proposed by Democritus. He rejected the notion of atomism in favor of a continuum. He also rejected determinism. He believed there were both animate and inanimate objects. Animate objects behave generally non-deterministically. Aristotle also accepted the notion of a soul in living beings. These must be present in their matter. We will now present a number of views, whenever possible using the author's original statements, on issues related to the measurement problem. The first of these areas is non-determinism. But chance also and spontaneity are reckoned among causes. Many things are said both to be and to come to be as a result of chance and spontaneity. Others there are who indeed believe that chance is a cause, but that it is inscrutable to human intelligence as being a divine thing and full of mystery. Chance and what results from chance are appropriate to agents that are capable of good fortune and of moral action generally. Therefore, necessarily chance is in the sphere of moral actions. An inanimate thing, or a lower animal or a child, cannot do anything by chance, because it is incapable of deliberate intention. The spontaneous, on the other hand, is found both in the lower animals and in many inanimate objects. Had Aristotle been alive to see the developments of quantum mechanics, he probably would have argued that Schrödinger's wave equation would not be by itself sufficient to describe the universe, as there is no chance inherent in unitary evolution. We now turn to Aristotle's views concerning epistemology. All men by nature desire to know. An indication of this is the delight we take in our senses. Further, if we admit in the fullest sense that something exists apart from the concrete thing, whenever something is predicated of the matter, must there, if there is something apart, be something apart from each set of individuals, or from some and not from others, or from none? If there is nothing apart from individuals, there will be no object of thought, but all things will be objects of sense. And there will not be knowledge of anything, unless we say that sensation is knowledge. And in general, if only the sensible exists. There would be nothing if animate things were not, for there would be no faculty of sense. Now the view that neither the sensible qualities nor the sensations would exist is doubtless true, for they are affections of the perceiver, but that the substrata which causes the sensation should not exist even apart from sensation is impossible. For sensation is surely not the sensation of itself, but there is something beyond the sensation which must be prior to the sensation, for that which moves is prior in nature to that which is moved, and if they are correlative terms, this is no less the case. Had Aristotle been alive to see the developments in quantum mechanics, he probably would have argued that knowledge comes about only from sensing or measurement. Without sensation, there would be no knowledge. Furthermore, something external must cause a sensation other than the sensory system itself. Aristotle had rather detailed views on consciousness. 4. Our assumption is that things that are undergoing alteration are altered in virtue of their being affected in respect of their so-called affective qualities. Since that which is of a certain quality is altered in so far as it is sensible, and the characteristics in which bodies differ from one another are sensible characteristics. But the alteration of that which undergoes alteration is also caused by the above-mentioned characteristics, which are affections of some particular underlying quality. We see then that the animate is capable of every kind of alteration of which the inanimate is capable, but the inanimate is not capable of every kind of alteration of which the animate is capable, since it is not capable of alteration in respect of the senses. Moreover, the inanimate is unconscious of being affected by alteration, whereas the animate is conscious of it, though there is nothing to prevent the animate also being conscious of it when the process of the alteration does not concern the senses. Had Aristotle been alive to see the developments in quantum mechanics, he probably would have argued that living systems are distinguished from inanimate systems by the existence of senses, that only animate systems measure. That is, consciousness is a necessary condition for measurement. Moving right along, let us consider the subjects of potentiality and actuality. For the same thing can be potentially at the same time two contraries, but it cannot actually. They seem then to be speaking of the indeterminate, and while fancying themselves to be speaking of being, they are speaking about non-being, for it is that which exists potentially and not in complete reality that is indeterminate. From what has been said, then, it is plain that nature in the primary and strict sense is the essence of things which have in themselves, as such, a source of movement. For the matter is called the nature because it is qualified to receive this, and processes of becoming and growing are called nature because they are movements proceeding from this. And nature in this sense is the source of the movement of natural objects, being present in them somehow, either potentially or in complete reality. Further, one must observe that some causes can be expressed in universal terms, and some cannot. The proximate principles of all things are the this, which is proximate in actuality, and another which is proximate in potentiality. The universal causes, then, of which we spoke, do not exist. Aristotle, had he been alive when quantum mechanics was founded, might have associated the wave function as representing potentialities, whereas actualities occurred due to measurement. The two potential contraries expressed by Aristotle might be considered a superposition of two distinctly different potential outcomes. Aristotle probably would have associated sensing with measurement and actualization of a particular outcome or term in the superposition. A similar idea has been suggested by Heisenberg. When we began researching the history of the measurement problem, we didn't expect to see anything by Aristotle on entanglement. Yet there are statements that indicate that Aristotle wrote about systems that appear to be entangled. One might most readily suppose the parts of living things and the parts of the soul nearly related to them to turn out to be both, in other words, existent in complete reality as well as in potency, because they have sources of movement in something in their joints, for which reason some animals live when divided. Yet all the parts must exist only potentially when they are one and continuous by nature. Aristotle, had he been alive when quantum mechanics was founded, might have associated a pure entangled state as being whole or one, and the parts or subsystems as existing only potentially. This is because no subsystem of a pure entangled state can be specified in terms of a single pure state, only via a mixture, which always requires more than one pure state for specification. So in this sense, the subsystems can only exist potentially. Aristotle also examined the issue of absolute quantities versus relative quantities. Relative terms, which imply number or potency, therefore are all relative because their very essence includes in its nature a reference to something else. But that which is measurable or knowable or thinkable is called relative because something else involves a reference to it. The significance of absolute versus relative quantities is not yet fully understood in terms of measurable quantities. But Aristotle, if he were alive today, might argue that only relative quantities can be measured, as many quantities, such as the electromagnetic vector potential, can be changed by a gauge transformation and therefore are gauge dependent. Interestingly, Aristotle's reasoning appears to have led him to the anticipation of perishable and imperishable physics. But actuality is prior in a stricter sense also, for eternal things are prior in substance to perishable things, and no eternal thing exists potentially. The reason is this: every potency is at one and the same time a potency of the opposite. For while that which is not capable of being present in a subject cannot be present, everything that is capable of being may possibly not be actual. That, then, which is capable of being may either be or not be. The same thing, then, is capable both of being and of not being. And that which is capable of not being may possibly not be, and that which may possibly not be is perishable, either in the full sense or in the precise sense in which it is said that it possibly may not be. In other words, in respect either of place or of quantity or quality. In the full sense means in respect of substance. Nothing, then, which is in the full sense imperishable is in the full sense potentially existent, though there is nothing to prevent its being so in some respect, in other words, potentially of a certain quality or in a certain place. All imperishable things, then, exist actually, nor can anything which is of necessity exist potentially, yet these things are primary, for if these did not exist, nothing would exist. Aristotle, had he been alive when quantum mechanics was founded, might have associated the act of not being with the vacuum state, and the wave function collapse with the perishable nature of potentiality. He also could have associated nature's non-perishable aspects with the process of actualization. Aristotle put forth the concept of soul in living beings. Since some such originative sources are present in soulless things, and others in things possessed of soul and in soul, and in the rational part of the soul, clearly some potencies will be non-rational, and some will be accompanied by a rational formula. This is why all arts, in other words, all productive forms of knowledge, are potencies. They are originative sources of change in another thing, or in the artist himself considered as other. Some things can exist apart and some cannot, and it is the former that are substances. And therefore all things have the same causes, because without substances, modifications of movements do not exist. Further, these causes will probably be soul and body, or reason and desire in body. Aristotle appears to be contemplating something beyond substance called soul. The soul gives rise to non-rational potencies, and yet it is also possible for the potencies to change via a rational formula. Aristotle might therefore have associated Schrödinger's equation with the rational change of the wave function, And the non-rational changes due to a soul would perhaps be due to the non-deterministic changes of chance. Last but not least, Aristotle appears to have anticipated discontinuities in nature. Nor, again, can there be anything intermediate between that which suffers and that which causes increase, for the part of the latter that starts the increase does so by becoming attached in such a way to the former that the whole becomes one. Again, the decrease of that which suffers decrease is caused by a part of the thing becoming detached. So that which causes increase and that which causes decrease must be continuous with that which suffers increase and that which suffers decrease respectively. And if two things are continuous with one another, there can be nothing intermediate between them. In every case of such alteration, it is evident that the respective extremities of that which causes and that which undergoes alteration are adjacent. Thus, there can be nothing intermediate between that which undergoes and that which causes alteration. And this is evident from what happens in respect of sensation, for the same thing never appears sweet to some, and the contrary is sweet to others. Continuity here is being used as adjacent in time. It appears that what is being described are actually discontinuous processes, since they are all extremities and are adjacent. It may be that had Aristotle been alive when quantum mechanics was founded, he might have associated Planck's quantum of action with these discontinuities and concluded that because particles are quantized and indivisible, that this would require their entire absorption into the measurement device upon measurement in order to meet the requirement of becoming attached in such a way that the whole becomes one. Before moving on, let us remark that whether you agree or disagree with Aristotle on any particular issue, he does appear to be way before his time in the intensity and depth of consideration that he gave to the foundations of physics. Most likely not before Aristotle or even in contemporary times, other than perhaps Niels Bohr, does anybody appear to have given such far-reaching considerations to physics. Epicurus, perhaps in response to the criticisms of Aristotle, modified Democritus's deterministic theory. He included swerving so that the atoms do not necessarily take a straight line path. This appears to take into account the possibility of free will and non-determinism. He proposed three causes for motion: necessity, chance, and our own agency. After the Greek philosophers Aristotle and Epicurus, the study of physics largely, but not entirely, moved toward the discoveries of mathematical formulas or deterministic laws and rejection of major portions of Aristotle's theory. The ideas of classical physics were put forward by the Greek and Roman Stoic philosophers that came after Aristotle and can be summarized by Chrysippus in 280 BC. For there is no such thing as lack of cause or spontaneity in the so-called accidental impulses which some have invented. There are causes hidden from our sight which determine the impulse in a definite direction. In the 15th through 17th century, the astronomical work of Copernicus, Kepler, and Galileo gained fame, which was largely mechanical in nature. Newton and Maxwell also formulated their work during this time period, and it also was via mechanical formulas. And the philosophy of Hume and Hobbes and others, representing the compatibilist viewpoint, that free will is compatible with deterministic laws, was put forward during these times. In terms of religious organizations, views on predestination existed in certain Reformed Protestant Christianity religions. However, other religious views existed, including the Catholic view espoused by St. Thomas Aquinas, who was influenced largely by Aristotle. This work and these discoveries were largely a movement that provided a foundation for which inductive reasoning flourished. Perhaps this is best characterized by Laplace's statement in 1814. We may regard the present state of the universe as the effect of its past and the cause of its future. An intellect which at a certain moment would know all forces that set nature in motion and all positions of all items of which nature is composed. If this intellect were also vast enough to submit these data to analysis, it would embrace in a single formula the movements of the greatest bodies of the universe and those of the tiniest atom. For such an intellect, nothing would be uncertain, and the future, just like the past, would be present before its eyes. Even though the movement in physics from the 16th through the 19th century was largely toward mechanistic, classical theory and inductive thought, there generally remained a group that to some extent continued to follow the views of Aristotle. Descartes, from 1596 to 1650, had a similar but slightly different view than Aristotle. Examples of these views include Descartes and Kant. Descartes proposed a mind-body separation. The mind is indivisible. The body is divisible. I think, therefore I am. Kant, between 1724 and 1804, did not agree with the compatibilist viewpoint. We now turn to the theory of thermodynamics. Carnot, in 1824, proposed a macroscopic theory of the work that can be extracted via use of hot and cold bodies in terms of caloric systems. Largely, the deterministic classical movement was maintained, although certain questions remained regarding irreversibility and thermodynamics. Classical physics did not fully explain macroscopic effects of temperature and mixing. A prime example of this is Maxwell's demon. Practical irreversibility was added due to the property of mixing. Boltzmann, Gibbs developed and applied the theory of entropy. Following the formulation of energy conservation by Joule in 1845, Boltzmann in 1860s and others developed kinetic theory based on the concept of atomism of earlier workers as originally proposed by Leucippus and Democritus. This was opposed by most philosophers and many scientists at the time, such as Mach. Boltzmann's statistical mechanics was considered to obey deterministic laws, but for simplicity was modeled using probability. A major paradigm shift in physics started anew with Planck's discovery of the quantum of action H in 1900. This was developed to explain blackbody radiation. Physical action must be a multiple of H for a given electromagnetic frequency, hence action is quantized. This led to the development of quantum theory by Bohr, Einstein, and others. An explanation of the photoelectric effect was postulated by Einstein in 1905, that there are individual light particles that carry energy E equals h nu. This extended Democritus's and Boltzmann's atomism to light. Previously, light was understood as a wave in optics. Largely after this discovery that the problem of wave-particle duality began to be formulated. Niels Bohr was a leader in the tremendous advancement in the fundamental efforts on atomic physics and quantum mechanics. He was a student through 1910. The two brothers, Niels and Harold, were admitted as silent listeners to philosophical conversations of their father and his friends. And this first confrontation with the epistemological problem of biology, in which apparently conflicting views were found equally indispensable for a full understanding of the phenomena, made a lasting impression upon Niels's mind. At that time, I really thought to write something about philosophy, and that was about this analogy with multi-valued functions. And the point is that if you try to say you now have two values, let us say of square root, then you can walk around in the plane because if you are in one point, you take one value, and there will be at the next point a value which is very far from it and which is very close to it. Probably the only answer is that emotions, like cognition, must be arranged in planes that cannot be compared. His doctoral dissertation was a purely theoretical work, The Electron Theory of Metals. This theory accounts qualitatively for the most varied properties of metals, but it ran into many difficulties as soon as a quantitative treatment was attempted on the basis of the then accepted principles of classical electrodynamics. The very rigor of his analysis gave him, at this early stage, the firm conviction of the necessity of a radical departure from classical electrodynamics for the description of atomic phenomena. Bohr considered the quantum of action to require a distinct physics. This physics is characterized by discontinuities, non-determinism, whereby non-classical physics is due to the quantum of action, and in a manner that consciousness and volition are related to the quantum of action. In 1911, the atomic nucleus was discovered by Rutherford. Bohr, in 1913, published On the Constitution of Atoms and Molecules, Part 1, 2, and 3, in which he developed fundamental quantum postulates and made many new predictions in the papers concerning radiation from atoms. Two quantum postulates were put forward to describe light emission from atoms. 1. That the dynamical equilibrium of the systems in the stationary states can be discussed by help of the ordinary mechanics, while the passing of the systems between different stationary states cannot be treated on that basis. 2. That the latter process is followed by the emission of homogeneous radiation, for which the relation between the frequency and the amount of energy emitted is the one given by Planck's theory. The first assumption seems to present itself, for it is known that the ordinary mechanics cannot have an absolute validity. The second assumption is an obvious contrast to the ordinary ideas of electrodynamics, but appears to be necessary in order to account for experimental facts. Substantial progress was made in confirming experimentally Bohr's theory and also explaining various effects in terms of quantum mechanics. Many experiments were performed that confirmed spectroscopically the prediction of Bohr's model via quantum mechanical postulates. The Stark effect, which was discovered in 1914, was explained via quantum mechanics in 1916. The Zeeman effect, which was discovered in 1897, was also explained via quantum mechanics in 1917. And Stern-Gerlach experiments were performed in 1922. The correspondence principle was put forward by Bohr and summarized in his 1922 Nobel lecture. According to the correspondence principle, it is assumed that every transition process between two stationary states can be coordinated with a corresponding harmonic vibration component in such a way that the probability of the occurrence of the transition is dependent on the amplitude of the vibration. This appears to have often been misinterpreted by many. For example, Bohr includes low quantum numbers in his definition above, and not only high quantum numbers, which would correspond to the classical. Many people often refer to Einstein and Bohr's famous arguments during the Solvay conferences of 1927 and 1930, where Einstein and Bohr famously debated the issues of complementarity. However, it is known that causality and other issues of whether the quantum exists as a wave or particle, or the wave-particle duality problem, was actually considered rather early on by Einstein and Bohr in the 1920s and perhaps earlier. In a 1920 letter to Born, Einstein states, "That business about causality causes me a lot of trouble too. Can the quantum absorption and emission of light ever be understood in terms of the complete causality requirement, or would a statistical residue remain? I must admit that there I lack the courage of my convictions, but I would be very unhappy to renounce complete causality. In my spare time, I always brood about the problem of quanta from the point of view of relativity. I do not think that the theory can work without the continuum, but I do not seem to be able to give tangible form to my pet idea, which is to understand the structure of the quanta by redundancy and determination using differential equations." Bohr, before 1925, insisted that the frequency nu appearing in the energy E equals h nu of the quantum is defined by experiments on interference phenomena, which apparently demand for their interpretations a wave constitution of light. And light quantum theory thus makes nonsense of its own basic equations. Bohr was for a long time against Einstein's corpuscular particle theory of light. Bohr and others put forward BKS theory in 1924 to utilize only waves and not particles. However, the theory required that energy not be conserved on every individual scattering event, but only on average. In 1925, Compton performed experiments that showed that energy and momentum were conserved on every trial, even down to the single quanta. This established that Einstein's light quanta really existed. Bohr wrote to Rutherford telling him how miserable he was. But Bohr eventually accepted the existence of light quanta and abandoned BKS. Schrödinger, in 1926, discovered what was to become known as the Schrödinger equation. He introduced a wave function psi t that deterministically evolves as a function of time. Psi t is complex, and the rate of change of psi t is proportional to the energy, or Hamiltonian, times psi. Eigenstates of the equation represent Bohr's stationary states. Corresponding eigenvalues of the equation correspond to the energies of the respective stationary states. This was shown to be mathematically equivalent to Heisenberg's matrix mechanics, introduced before Schrödinger's equation, but quickly became preferred over Heisenberg's matrix mechanics for most problems. Schrödinger's equation was utilized shortly thereafter to compute the energies of the atomic transitions and to many other problems. Schrödinger desired that his equation would govern all particles in matter. A meeting took place between the two men at Bohr's home in September 1926. It is said to have gone something like this. Schrödinger: surely you realize that the whole idea of quantum jumps is bound to end in nonsense. You claim first of all that if an atom is in a stationary state, the electron evolves periodically, but does not emit light. Next, the electron is said to jump from one orbit to the next and to emit radiation. Bohr: what you say is absolutely correct, but it does not prove that there are no quantum jumps. Schrödinger: the moment, however, that we change the picture and say that there are no discrete electrons, only electron waves or waves of matter, then everything looks quite different. The emission of light is as easily explained as the transmission of radio waves through the aerial of the transmitter. Bohr: I beg to disagree. Just take the case of thermodynamic equilibrium between the atom and the radiation field. This derivation demands that the energy of the atom should assume discrete values and change discontinuously from time to time. In 1927, Heisenberg introduced the uncertainty relationships. These relationships were utilized substantially by Bohr in order to provide justification of the claim that causal space-time coordination that was envisioned by Einstein is impossible. One cannot have particle trajectories x, y, z, and t that can be known. And this is because any closed system must interact with a measurement device in order to determine a given quantity. Because of this interaction required for measurement, the system is no longer closed, and one must take into account the effect of the interaction between system and measurement device. The effect of the measurement device is to create a disturbance of the original system. This necessary disturbance was historically thought of as relating to the uncertainty principle. For example, by measuring x precisely, the device in its interaction with the system makes the momentum uncertain. However, the fine points of this issue are still being debated in the literature. It appeared early on to Bohr and others, shortly after Schrödinger put forward his wave equation, that Schrödinger's equation would not alone suffice to fully explain measurement phenomena. Born shortly proposed his Born law in the same year as Schrödinger's equation to explain the non-deterministic, probabilistic outcomes that occur in experiments. Born initially considered the possibility that there was an underlying hidden variable model. Here, the whole problem of determinism comes up. From the standpoint of our quantum mechanics, there is no quantity which in any individual case causally fixes the consequence of the collision. But also experimentally, we have so far no reason to believe that there are some inner properties of the atom which condition a definite outcome for the collision. Ought we to hope later to discover such properties, like phases or the internal atomic motions, and determine them in individual cases? Or ought we to believe that the agreement of theory and experiment as to the impossibility of prescribing conditions for a causal evolution is a pre-established harmony founded on the non-existence of such conditions? I myself am inclined to give up determinism in the world of atoms, but that is a philosophical question for which physical arguments alone are not decisive. However, after the concept of complementarity and the Copenhagen interpretation was firmly established, he rejects determinism. And here, from Born's Nobel lecture in 1954, he says, "I should like only to say this. The determinism of classical physics turns out to be an illusion, created by overrating mathematical-logical concepts. It is an idol, not an ideal in scientific research, and cannot therefore be used as an objection to the essentially indeterministic, statistical interpretation of quantum mechanics." As a result of attempting to reconcile the concepts of Schrödinger's unitary evolution, Born's law, and Heisenberg's uncertainty relationships, Bohr and his followers formulated what became known as the Copenhagen interpretation. We summarize the Copenhagen interpretation as follows. Stationary states are states that can be occupied. They are non-classical, as classical treatments of an electron orbiting the nucleus generally will not give a correct physical accounting. As a consequence of Planck's quantum of action, when matter changes from one stationary state to another, it emits a photon which has energy that corresponds to the difference of the energy of the two stationary states. Discontinuities exist as matter jumps from one stationary state to another stationary state. There are physical uncertainties due to the interaction of measuring device and system. No causal space-time description is knowable. The best that can be known is a statistical account. Statistics are used in order to predict the frequency of occurrences of measurements. Complementarity is a concept that is often heard to be confusing or difficult to grasp. Rather than try and come to terms with complementarity in the most detailed sense, we will consider a broad definition given by Bohr that we believe can be well understood. Complementary in the sense that any given application of classical concepts precludes the simultaneous use of other classical concepts which in a different connection are equally necessary for the elucidation of the phenomenon. In this sense, complementarity is enforced by the uncertainty relationships where one can only know very accurately the position of the particle by a large uncertainty in the momentum, or one can know the particle's energy but with a large uncertainty in time, and vice versa. This infers that it is impossible to know a particle's trajectory, or that the causal space-time coordination envisioned by Einstein is impossible to know. Also, it can be applied to the wave-particle duality problem, as Bohr states. While energy and momentum are associated with the concepts of particles, and hence may be characterized according to the classical point of view by definite space-time coordinates, the period of vibration and wavelength refer to a plane harmonic wave train of a limited extent in space and time. Wave properties and particle properties are dual or complementary properties related to the interaction of particle and device during measurement. Additionally, Bohr applies complementarity to the problem of consciousness and free will. One simply cannot know all parameters associated with a space-time description because the process of knowing requires measurements or interactions with a device. So the uncertainty relationships are a natural artifice that reinforces Bohr's physics. For example, we have already seen that Bohr relates the wave-particle duality problem to the uncertainty relationship, but he also states it is probable that the chasm appearing between these two different conceptions of the nature of light, corpuscular and wavelength, is an evidence of unavoidable difficulties of giving a detailed description of atomic processes without departing essentially from the causal description in space-time that is characteristic of the classical mechanical description of nature. There were a number of quantum mechanical developments between 1924 and 1934. In 1924, de Broglie proposed the theory that not only light, but matter could also be seen as waves. In 1925, Pauli formulated the fermion exclusion principle. In 1927, Dirac extended Bohr's work on matter and developed the quantum theory of light based on quantizing Maxwell's equations. In 1927, Pauli works out the mathematical theory of spin. In 1928, Dirac developed the relativistic extension of Schrödinger's equation applicable to fermions. He incorporated Pauli's theory of spin, and he also made predictions of antimatter. In the 1930s and onward, Bohr and Rosenfeld examined measurable properties of the electromagnetic field. 1935 was a rather noteworthy year for issues in the foundations of quantum mechanics. John von Neumann developed a mathematical foundation of quantum mechanics, which is largely in use today. He formulated two postulates: a measurement postulate applied when a measurement is made, and a postulate of Schrödinger unitary evolution otherwise. This mathematical theory allowed multi-particle entangled states to be analyzed and characterized in terms of their individual subsystems. Schrödinger published his famous CAT paper that codified the modern measurement problem. Schrödinger introduced the concept of entanglement in his arguments. He developed a more in-depth understanding of separated entangled systems in the paper Discussion of Probability Relations Between Separated Systems. He discusses non-locality of systems due to entanglement, but Schrödinger disliked this feature of his equation. This paper was perhaps the first quantum information paper. Non-locality of separated systems was to become the forerunner of teleportation. Einstein, Podolsky, and Rosen developed the EPR argument against non-locality or action at a distance. We will now consider separately the principal progenitors of quantum mechanics, Einstein and Bohr. Einstein believed that particles in nature follow distinct paths or have space-time coordination. This was assumed in Einstein's theory of special relativity. Einstein did not believe that physics had a probabilistic component. He was famous in saying, "God does not roll dice." Einstein is often not associated with the modern development of quantum mechanics due to his EPR arguments that were successfully rebutted by Bohr. Yet, it was Einstein's discovery of the photoelectric effect in 1905, which implied that there is a particle aspect to light. Einstein originated the concept of an underlying ghost field in the 1920s that guides particles in a manner to explain the wave properties and subsequent particle occurrences during measurement via a probabilistic accounting. Einstein is credited by Heisenberg in 1927 as first formulating the statistical interpretation of de Broglie waves in 1925. This highly influenced Bohr. Einstein's 1925 paper, Quantum Theory of a Monatomic Ideal Gas, where he calculates the fluctuations in the number of particles per volume, has two terms. One term is particle-like, and the other is wave-like, giving a wave-particle duality to this quantity, similar to the wave-particle duality Einstein first found for light in 1909. Einstein noted, "Thus, in addition to deflections due to collision in accord with classical mechanics, mechanically inexplicable deflections of the molecules also will occur with frequency comparable to the former." Einstein desired fundamentally deterministic particle motion. Early in 1926, he was enthusiastic, but quickly saw that Schrödinger's equation ultimately produced superposition solutions that would be problematic and not correspond to nature. He did not like the measurement postulate of Bohr as it indicated instantaneous action at a distance. Einstein influenced Schrödinger's cat. Einstein wrote to Schrödinger describing an unstable gunpowder keg that would eventually be in a superposition of having both unexploded and exploded states. Einstein never accepted the Copenhagen interpretation. He worked on a deterministic unified causal solution using overdetermined equations that would yield singularities or discontinuities even as early as 1920. Einstein listed a number of reasons as to why he rejected Bohr's interpretation, the principal reason being that a final abandonment of strict causality is very hard for me to tolerate. Many authors often ignore the issues of consciousness and free will when discussing Bohr. Some believe that these issues were prominent only in Bohr's early years, but were abandoned later and replaced with Heisenberg's uncertainty relationships. Emphasis is often placed on the Bohr-Einstein debates in historical essays. In our view, this leaves a substantial hole in one's understanding of Bohr's philosophical conceptions of nature. We will now examine Bohr's position on a range of issues concerning causality, life, free will, and consciousness. On non-causality in life, I am particularly concerned to emphasize that, epistemologically speaking, a natural place can be found in our worldview for the laws obeyed by the phenomena of life. I agree, of course, with the point that it is above all the fundamental limitation of the applicability of the causality concept in the inorganic macrocosms which gives us the necessary freedom, and that, in this sense, acausality can be regarded as a characteristic of life. The peculiar reaction of the organism is, however, connected in the closest possible way with the laws of biology, which cannot be comprehended mechanically, and is therefore different in principle from the technical amplification devices used in the study of fluctuation phenomena. Just as the stability of atomic phenomena is inseparably connected with the limitation of observation possibilities expressed by the uncertainty principle, so, in my view, the peculiarities of life phenomena are connected with the impossibility, in principle, of ascertaining the physical conditions under which life exists. Briefly, one could perhaps say that atomic statistics deals with the behavior of atoms under well-defined external conditions, whereas we cannot define the state of the organism on an atomic scale. On Life and Individuality and Wholeness, in Niels Bohr's collected works, Volume 10, Complementarity Beyond Physics, it is stated by the editors regarding Bohr's view, mechanism must not only explain how the different parts of the human body function in order to maintain its existence through the best possible adaptation to constantly changing conditions. It must also be able to explain the wholeness, the unity, and the individuality of a person. This is the problem ultimately facing mechanism. It must be able to give a physical, chemical account, even of a conscious living organism, because whatever consciousness may be, it is an inseparable feature of such an organism. On the issue of free will, Bohr has this to say. To illustrate such argumentation, we may refer to the old problem of the freedom of will. In an unrestricted deterministic approach, this concept, of course, finds no place, but it is evident that the word volition is indispensable in an exhaustive description of psychical phenomena. We are so far removed from a causal description that an atom in a stationary state may in general be said to possess a free choice between various possible transitions to other stationary states. Bohr, regarding conscious experience and measurement, makes the following statements. From a biological point of view, we can hardly interpret the characteristics of psychical phenomena except by concluding that every conscious experience corresponds to a residual impression in the organism, amounting to an irreversible recording of the outcome of processes in the nervous system which are not open to introspection and are hardly adapted to exhaustive definition by mechanistic approach. The unavoidable influence on atomic phenomena caused by observing them here corresponds to the well-known change of the tinge of the psychological experiences. Because Bohr uses every conscious experience amounts to an irreversible recording, he is making the argument that conscious experience is a sufficient condition for measurement. On the issue of the relationship between consciousness and free will, Bohr has the following to say. It may be stressed, however, that the concept of complementarity is also suited to characterize essential aspects of the consciousness associated with our life. It is on this background that we may speak in a rational manner about volition as an indispensable element in any attempt at an exhaustive description of consciousness. Regarding the investigation of the foundations of life, Bohr and Pauli worked with Max Delbruck in 1932, where Delbruck heard Bohr's Light and Life lecture, where Bohr put forward parallels between quantum physics and biology. Delbruck worked with biologists to determine if quantum mechanics was responsible for stability and mutability of genes. Bohr did not abandon his views on the relationship between the quantum of action and consciousness in later life. Quite the opposite. Delbruck tried to find complementary relationships and paradoxes in biology. He maintained correspondence with Bohr until Bohr's death in 1962. The finding of a classical action in the discovery of DNA was a blow to Bohr. Undoubtedly, it was the discovery of the helical DNA structure in 1953 and the subsequent understanding of the genetic code that made Bohr modify or withdraw some of his arguments. The mechanism of replication was in fact discovered and explained without knowledge of what happens at the atomic level in the organisms. From an epistemological point of view, the double helix was trite. It raised no paradoxes. It required no new laws. Physical and chemical explanations were found to be quite sufficient to account for one of the fundamental secrets of life. Bohr, as he had done when he was wrong in his BKS argumentation, deductively shifts his hypothesis from life beginning at the gene level to life beginning at the cellular level. The constancy peculiar to species is undoubtedly closely connected to the atomic stability of the chromosomes of the cells. However, it is just as important to bear in mind that in a living organism, we are never dealing with chromosomes alone, but that the smallest units that can be considered in reproduction are those cells in which the wonderful divisions and couplings of chromosomes take place by means of the necessary nutrients and enzymes. But although there exists already a tradition of the biologists of California to disagree with Bohr, it cannot be denied that Bohr is right when he emphasizes that the smallest living unit is the cell and not the isolated chromosome. Bohr died in 1962, with his desired deep understanding of life not having been fulfilled, at least to the extent that Bohr had contributed to the understanding of atomic physics. In this area, Bohr suffered a similar fate as Aristotle. It appears that Bohr was well before his time. Unfortunately, the quantum contemporaries of Bohr did not take up the investigation of the foundations of life to any significant extent until Roger Penrose rose to the occasion and picked up the subject matter anew in his book The Emperor's New Mind in 1989. An important historical question that we will now examine in some detail is whether or not Bohr has shown that quantum evolution necessarily is non-deterministic, or whether there still could exist a deterministic but unknowable substratum to explain physics. In a supplement to Nature published in 1928, Bohr writes, "Strictly speaking, the idea of observation belongs to the causal space-time way of description. Due to the general character of relation 2, which is the uncertainty relation, however, this idea can be consistently utilized also in the quantum theory if only the uncertainty expressed through this relation is taken into account. As remarked by Heisenberg, one may even obtain an instructive illustration to the quantum theoretical description of atomic, microscopic phenomena by comparing this uncertainty with the uncertainty due to imperfect measurement, inherently contained in any observation, as considered in the ordinary description of natural phenomena." Continuing in the same paper, Bohr writes, "According to the quantum theory, just the impossibility of neglecting the interaction with the agency of measurement means that every observation introduces a new, uncontrollable element. Indeed, it follows from the above considerations that the measurement of the positional coordinates of a particle is accompanied not only by a finite change in the dynamical variables, but also the fixation of its position means a complete rupture in the causal description of its dynamical behavior, while the determination of its momentum always implies a gap in the knowledge of its spatial propagation." Bohr's use of strictly speaking, when speaking of observation as a causal process, supports the contention that Bohr believes that closed systems are causal, and because an interaction is required during measurement with an external device, the system being measured is no longer closed but open, and for which the results are uncontrollable and have an apparent non-deterministic appearance. The wave function must evolve to have an increasing width or uncertainty in one variable when a conjugate variable evolves to become more certain. As the wave function always obeys Heisenberg's uncertainty relationships, even in Schrödinger evolution, it would be non-classical in that one cannot define an absolute space-time trajectory as simultaneous specification of conjugate quantities is required. Additionally, Bohr and Heisenberg and others considered the possibility of a deterministic substratum. Continuing, is Copenhagen fundamentally non-deterministic or unknowable but underlying deterministic. No rigorous theoretical argument appears to be given by Bohr to justify fundamental nondeterminism versus unknowable determinism. Deterministic evolution is consistent with the requirement of loss of phase that would result due to an uncontrollable interaction. Possibility for space-time description closely connected with conservation theorems. Measurement of energy or momentum with given accuracy implies loss of phase relations, which implies impossibility of interference by superposition. This was found in the draft Gummel lecture by Bohr in Bohr's Collected Works, Volume 6. Thus, one can pursue the reciprocity of the concept of individuality and the superposition principle to far-reaching consequences. One can show in general that any use of the former concept limits the application of the latter principle as an immediate consequence of the loss of phase resulting from every observation. It is well known that the loss of phase, or a mixture, also results in standard decoherence theory using deterministic evolution via Schrödinger's equation when considering system measuring device interaction. So, does Bohr believe that the use of probability is fundamental, or is being used because the underlying theory is deterministic, but of such complexity that the use of probability is a good approximation? However, it is most important to realize that the recourse to probability laws under such circumstances is essentially different in aim from the familiar application of statistical considerations as practical means of accounting for the properties of mechanical systems of great structural complexity. In fact, in quantum physics, we are presented not with intricacies of this kind, but with the inability of the classical frame of concepts to comprise the peculiar feature of indivisibility or individuality, characterizing the elementary processes. Bohr claims that the use of probability is not to account for mechanical systems of great complexity. But why should quantum physics not be able to capture such intricacies? Bohr appears to believe that discontinuities were real and that nondeterminism was physical, but only when open to direct observation. Still, it would appear that the essence of the theory may be expressed through the postulate that any atomic process open to direct observation involves an essential element of discontinuity, or rather individuality, completely foreign to the classical ideas and symbolized by Planck's quantum of action. This postulate at once implies resignation as regards the causal space-time coordination of atomic phenomena. So we are seeing the issue of being open to direct observation is clearly a distinction for Bohr. Also, a detailed investigation of the process of the brain is excluded on account of the quantum of action. We must expect, he says, that an attempt to observe the processes in the brain will bring about an essential alteration in the awareness of volition. The argument appears to allow the possibility that closed systems obey Schrödinger's equation, but are fundamentally unknowable due to interaction during measurement in order to observe such systems. A completely deterministic description of human conduct would require a knowledge of the so-called internal and external preconditions, which are in principle mutually exclusive, and precisely in this situation should allow natural room for the immediate feeling of will. Similar arguments by Bohr center around the inability to determine the initial state of a system without affecting it due to the interaction with an external measurement device. The conception of a stationary state involves, strictly speaking, the exclusion of all interactions with individuals not belonging to the system. The fact that such a closed system is associated with a particular energy value may be considered as an immediate expression for the claim of causality contained in the theorem of conservation of energy. This is again an argument that is consistent with causal or deterministic evolution for closed systems. Bohr's arguments appear to only require the condition of deterministic but unknowable evolution for closed systems. From 1935 into the 1960s, fundamental problems diminished in importance, as Dirac stated in 1929. The underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known, and the difficulty is only that the exact application of these laws leads to equations much too complicated to be soluble. To think that when beginning from a point in 1900 where it was believed there were no atoms but a continuum, to whereby one knows all underlying physical laws in a span of only 29 years, well, can perhaps best be described by examining all synonyms of presumptuous. Feel free to type synonyms of presumptuous into Google search and see what you get. The fundamental non-determinism, discontinuities, and causal renunciation of Bohr, Born, and others continued to diminish in importance as new faces appeared who began to largely calculate and explain finer and finer effects. Schwinger, Feynman, Bethe, etc. The development of QED, lamp shift theory, found the measured shift due to the electromagnetic field interaction, development of new applications in fields of quantum electronics, quantum optics, etc., that produced new devices based on quantum mechanics. Very few modern researchers appear to fully grasp the measurement problem, and often believe that the universe is described completely by Schrödinger's equation. This is a major step backward on the measurement problem, as few researchers and fewer students concentrated on this problem. This attitude is perhaps best epitomized by the term "shut up and calculate," which is largely the opposite of a rallying cry for students to investigate the measurement problem. John Bell, in 1964, developed his now famous Bell inequality. Bell's inequality shows that entangled states cannot be interpreted as having an a priori initial state for which the results of the measurement are only a function of the respective detector settings and the initial state, and that entangled states must act non-locally under fairly general assumptions. I think it fair to say that if Bohr were alive to see Bell's inequalities, he would have gone outside and smoked his pipe in celebration. From approximately 1994 onward, the era of quantum information began. Numerous experiments have been performed to test the entanglement predictions of Schrödinger's equation. Bell's inequality has been verified to be violated in confirmation of non-locality, although all loopholes have not been closed. Applications using entanglement in quantum computing and communication have been developed. Mesoscopic physics has been investigated. Several experiments have been done that are significant regarding the physics of measurement. The measurement problem is rich in history. We have tried to present an unbiased opinion, in other words, without censure of the areas of consciousness and free will, of the issues that were historically considered by the major progenitors of quantum mechanics. In order to seriously examine the measurement problem, we believe one should arm oneself with as many tools as possible. The fullest possible understanding of the problem, as well as understand the historical issues so that one can avoid the mistakes of the past and develop a correct approach. This video is a companion to our book, The Quantum Measurement Problem, published by Inspire Institute and available at Amazon.com. This book is the first volume of a book series entitled Progress on the Physics of Quantum Measurement. Be sure to visit our website, which has more videos and additional information on the quantum measurement problem at theqmp.com. We also have been working a long time on our own approach to resolving the measurement problem that involves closed systems that function as measurement devices. The details of the approach can be seen at internon.com. You know, Ron, we finished this video on February 25th. And do you know what day February 25th is?
Oh, February 25th. Actually, it was that day in 1616 that the Inquisition ordered Galileo to stop insisting that the Earth moves. So an ominous day for science.
Well, yes. And it also happens to be the birthday of my dog. Can you guess, Ron, what the name of my dog is?
Let me think. What would Mike name his dog? Is it Internon?
Yes, right again, Ron. And we made this short video to celebrate Internon's birthday.
It's your birthday. Happy birthday. It's your birthday. Happy birthday. It's a great day. That's what we say. Happy birthday to you.
Entered on OG.
It's your birthday. Happy birthday. It's your birthday.